All right, y'all. So regardless of how you chose to approach this, whether you are continuing with the notes page that you already started, or whether you are starting with a clean sheet, guys, the topic for today is naming salts. I think, well, maybe you remember last time in class I mentioned to you that we're taking what we normally do in one day and we're splitting it in half. And actually, it's funny, literally splitting it in half, right? We drew a vertical line through our homework assignment and we only did the stuff on the left, splitting it in half. Well, guys, what we're going to do now is we're going to learn the things that we need to do the right side. So in order for this to work for you, what I want to do is I want to bring us back to what we did on the left side and then use that as a foundation for what we did on the right side. So guys, if these are easy for you, please do them anyway, because it sort of begins the conversation. If you don't know how to do these, one, you need to watch the screencast, but two, at some level, we can answer questions if you need. So guys, please do these. Write the chemical formulas for nickel 2 nitride and aluminum sulfate, sulfite. If you can do these, do them in your notes. If you can do these, you can say with a fair level of certainty, you're exactly where you need to be right now. If you can't do these right now, guys, you've just identified something that you need to get up to speed on. Now, if you've been watching the screencast, that means you need to come and talk with me because you're not learning this stuff and you've tried. If you haven't watched the screencast, then that responsibility lies on you to watch them and figure out how to do these. Once you've watched the screencast, if you still have questions, please come and talk with me. But you've got to do your part to get caught up. Wait a second, are you expecting students to actually engage and be an active participant in their learning? No. Sorry. Sarcasm feels good sometimes. Nickel 2 nitride, aluminum sulfite. So guys, obviously we're going to step through these in a minute. All right. So guys, here's what I'd like. Did you have enough time? You guys okay? All right, so here's what I want you to do. Compare your answers with the person sitting next to you. If your answers are different, figure out which one of you is right. Check them out. Or maybe you're both wrong. That could be too. Did you see what I did? I just pulled the animations out of this. I'm realizing I'd rather write these out than do the animations. I feel like there's better modeling that happens that way. Oh, still frozen. Like, what is happening? All right, guys, you good to go? So, if you would humor me for just a second, guys, you know there's a method to our madness, and I'm not here to waste your time. But what I want to do is I want to create a shared understanding of what we're doing so that we can use it as our jumping off point for what we're doing next. So guys, I'm going to do this way slower than probably most of you need to. The reality of it is if you can just write down the answers, that's awesome. If you need to do intermediate things, that's fine, and I'm going to. But guys, if you can cut straight to the answer, that's best. But if you need the structure, guys, we've got nickel, which is Ni. Now realize, and it's got to be big N, little I, right? No room for your little creative twists. Guys, big N, little I. But we don't even need to look up the charge, do we? What does the Roman numeral tell us? It's +2. That's brilliant. No. So understand these are rules and structures that are put together by, it's called the International Union of Pure and Applied Chemistry. They're the ones that actually get to decide what the processes are in chemistry. And the answer is no. So why don't we need Roman numerals in this? And the reason is because, negative Roman numerals. And the reason is because the negatives are the nonmetals, right? And with the exception of nitrogen, all of them can only have one negative charge. So we don't need to indicate what that would be because we don't have choices. Nitrogen's a little tricky, and there's different ways to deal with it, but we're not going to have to run into that. So, all right, you guys good on, and please stop me when you need, nickel +2. Now, guys, I threw you a curveball. When you got to the second part of this, if you grabbed your ion chart, you missed it. Right? So, guys, if it ends in IDE, where are you going to find it? Periodic table with what three exceptions? Peroxide, cyanide, and hydroxide. But guys, this ain't one of the, did you underline those three on your paper? This ain't one of those. So guys, when we see ide, the first thing we think is element. And in this case, it's nitrogen. And interestingly, Michael's question led us to a point. Guys, is it -2 and -3? Are those the two charges? Which one did we agree we're going to use? -3. All right, so this is -3. Then, guys, I'm going to do it this way. 2 and 3 first meet up at 6. So then we ask ourselves, how many 2's make 6? And the answer, of course, is 3. And then, guys, how many 3's make 6? And, of course, the answer is 2. And that would be nickel 2 nitride. What's the stupid mistake you're going to make on the test? Guys, the stupid mistake you're going to make on the test is this. Nickel 2 nitride, you're going to be like, hey, yo, that means 2 nickels and 1 nitrogen. Guys, I see this all the time. The 2 does not tell you how many, it tells you the charge. We good on that? Okay. So guys, anything relative to that you need to talk about? Okay, then let's do the next one. So we look up aluminum. Guys, aluminum is element number 13, and it can only have a charge of +3. Now we've got an ite, right? That tells us where to look. Yellow sheet. But be careful, it's an ite and not an 8. That means fewer oxygens, so it's not SO4, it's SO3. So guys, this would be SO3, and its charge is -2. And again, this was a coincidence. They meet at 6. So this meets at ±6. So we need 2 aluminums, and then we've got SO3. But guys, remember, we need 3 of those, right? 3 -2's makes -6. How do we represent 3 of these? What do we need? Parentheses. So guys, this goes in parentheses. Hey, yo, that's aluminum sulfite. You good there as well? You're sure? Let's pause. So clarifying questions, anything you want to chat about? You okay? Okay. So guys, I've got an important question for you that's going to set the stage for the hard part of what we're about to do. Guys, why does this have a Roman, and I know we're beating a horse, right? But guys, why does the one on the left have a Roman numeral and the one on the right doesn't? What's true of the one on the left? More than one charge. Can you just say that in your brain like 11 times until you hear that? Because guys, that's going to be critical to what we're about to do. The ones that have Roman numerals have more than one charge. Aluminum can only be +3. And as a result, if you had put a Roman numeral in there, it'd be wrong because it's not necessary, because that's all it can be. You guys good on the ideas? Okay, now watch, guys. Here's what you've done up until now. You've done the left-hand side of that paper, and on the left-hand side of your homework, you were given 38. You were given 38 different chemical names, and you wrote the formulas. Guys, guess what we're going to do today? Yeah, exactly. This. Guys, you're going to be given the formulas, and you're going to come up with the names. We're going to do this in the other direction. Now, guys, what's going to make this hard? What's the tricky bit that's going to make this hard? And the answer is whether or not you need a Roman numeral. Because when you're given the formula and you're writing the name, the tricky bit is the Roman numeral. So again, why does this have a Roman numeral? More than one charge. You good? Okay. So guys, do this with me. Scratch it in your notes. We are done in 7 minutes. 8. This goes fast, y'all. So gang, here's what we're doing now. Today what we're going to do is we are going to name salts. These are the steps. Write them down. So guys, doing what you're going to do today. We're already to steps. We're almost done and we're just getting started. Remember guys, this is normally the second part of one big day. We broke it up. So guys, here's the deal. When you're naming salts, and guys, I would encourage you to write this sentence down word for word. You got to have that muscle memory experience here. When you're naming a salt, the first thing that you've got to do is determine whether the cation can have more than one charge. Have that experience. When you're naming a salt, that's what we're doing, right? We're flipping this around. We're naming salts. When you name a salt, the first thing you've got to do is determine if the cation can have more than one charge. When we're naming salts, the first thing you've got to do is determine if the cation has more than one charge. Yeah? Would you turn and explain to the person next to you why it matters? Guys, not a lot of chatter. It's not because you don't understand, it's because you're not making the connection. So guys, let's go backwards. Why? Oh, well, here, let me go back. This is going to freak out. Hold on. So guys, let's have the conversation again. Why does the one on the left have a Roman numeral and the one on the right doesn't? Because nickel can have more than one charge, yes? So why then is it important that the first thing we do is figure out whether the cation can have more than one charge? Because it tells us if we need a Roman numeral in the name. Are you making those connections? Okay, so guys, here's the deal. You're going to get really good at these, and you're going to get overconfident, and you're going to start writing chemical formulas, and you're going to skip this. And then you're going to be really frustrated when you have to do remediation after this test because you're like, oh crap, I put Roman numerals in everything and I didn't need to because some of them don't need Roman numerals because they can only have one charge. So guys, make sure you're doing this. So once you've done this then breaks this into two possible paths. We'll talk in a second. Is it critical to what I'm doing now? Okay. So guys, one of two things is going to happen, right? You're going to look on the periodic table and you're going to see something like aluminum. And aluminum can only have one charge. If it only has one charge, just name the stupid thing. What's the positive ion? What's the negative ion? Adding IDE and you're done. Because I'm going to show you an example of this in just a minute. Don't write it down, but I want to wait for you to get caught up. Is it okay? Can I ask kind of a screamingly obvious question? What's this? Table salt, which is actually what? Sodium chloride. Why do we not call it sodium 1 chloride? It sounds stupid, right? Why do we not call it, because sodium is +1. Why do we not call salt sodium 1 chloride? Look at sodium on the periodic table, element 11. Guys, looking at element 11 on the periodic table, how many charges can sodium have? One. And it is one, but it can only have one. Therefore, it doesn't need a Roman numeral because it can only be +1. So guys, we don't call this sodium 1 chloride because that's all sodium can be. Does that sentence that you wrote down now make sense? Okay. Now, what if we look and we find, come on baby, what if we look and we find that it can have more than one charge? So guys, if it can have more than one possible charge, you get to do some second grade math. If we find out that it can have more than one charge, you engage in a process that I call working it backwards. So guys, working it backwards, and I know I'm going fast, but just bear with me. 3-step process. Multiply, set it equal, and divide. That's it. It's kind of like the cover of Ed Sheeran's last 3 albums. Is that actually true? Why did that just come to my brain? Actually, I know why. I was on kind of an Ed Sheeran kick down in Mexico. Jesse was worried for me. I think that's true. Let's just stop there and call it a day, shall we? I'm disappointed you're not excited. All right, so guys, what if it can have more than one possible charge? Then what we're going to do is we're going to work this backwards. Now guys, the trick is this. You don't know what that means. And for me to try to explain this to you would be worthless right now because you have no context. So what we're going to do is we're going to work through 4 examples of these. When we're done with that, we'll bring out all the little tricky little twists. And then when we're done with that, we're going to do the same thing we did last time. We're going to turn to the right-hand side of that homework assignment, and you're going to do half of them. I don't know. We'll figure it out later. All right, here we go. So guys, 4 examples. Write this down with me. So guys, FeCl3. I actually almost said its name correctly because I just do this stuff in my head. So, what's the very first... We're going to name this, right? We're not going to call it FeCl3. So what we're going to do is figure out its name. To do that, what's the very first thing we've got to do? And look up in your page if you're not sure. You got to find iron on the periodic table and figure out whether or not it can have more than one charge. Now guys, again, I'm beating this horse, right? Stop. Why do we care if it can have more than one charge? What does that determine? Whether or not it needs a Roman numeral. And what do you see when you look at iron number 26? It can be 2 or 3. It needs a Roman numeral. So now the question becomes, which one? Guys, this is then what you do. Do this with me. Oh, for the love. Is this going to let me write? Okay. So guys, break it in half. Don't make the mistake of thinking you know how to do this just because you're watching me do it. Have the experience of doing it. So guys, we need to figure out if iron is +2 or +3. So in order to do that, we break this in half. And then here's what we do. You are going to work this backwards. Guys, watch. I'm going to try to draw this, but I'm afraid it's going to freak out. But let's see. So guys, literally, when you do this backwards, you're doing a backwards parabola. And it goes like this. You need a number, and then you're going to multiply, set it equal, and then you're going to divide. This is what the working it backwards process looks like. You're going to start in the upper right-hand corner with a number. You're going to multiply, set it equal, and divide, and that will give you the Roman numeral. So guys, let's do this. So the first thing we do, after we break it in half, go find the charge of chlorine, element number 17. There's like 6 different charges there. Which one do we use? -1. Why do we use the -1? Because it's the only negative charge, and the -1 is second. That's the non-metal. It's got to be negative. You good there? Now, multiply, set it equal, divide. So what are we going to multiply? So we're going to go -1 times 3. That's -3. So guys, we know the total negative charge in this salt is -3. So if the negative charge is -3, the positive charge has got to be +3 because salts have no total charge. But guys, how many iron atoms are creating that +3 charge? Just one. There's an understood 1 there. So 3 divided by 1 is 3. That means that this salt is iron 3 chloride. Now guys, I know this sounds horrible, but I don't even want to entertain questions right now. Typically what I find is that if this didn't make sense, simply seeing another example answers a lot of questions. So I'm going to move forward without asking for questions. Please trust me on this. We will stop, but let's not stop yet. Let's do one more to sort of get a little more exposure, and then we'll see where we're at. So guys, this is the next one we're going to do. Do it with me. Ni3 parentheses PO42. What's the very first thing we do, y'all? Look up nickel, find out if it can have more than one charge. Again, you're going to get lazy and you're going to skip this and it's going to bite you in the butt. Guys, find nickel in the periodic table. It is element number 28. What do we see? Do we need a Roman numeral? Yeah, we do. It's either going to be a 2 or a 3, but we don't know which one. So guys, what we're going to do is we're going to break this in half. Some of you see where this is now headed. Guys, we now need a number up here. We need the charge. But it's the charge of PO4, and where do we find that? On the yellow sheet. And you'll find that PO4, which is phosphate, is all by itself in the bottom right-hand corner. And what's the charge of phosphate? -3. Now, guys, watch. The first mathematical step is to multiply. How many phosphates do we have? How many phosphates do we have? 2. Guys, that's what that 2 tells you. That PO4 package has a charge of -3, but we have 2 of them. Guys, stop. Make sure that makes sense. We have 2 of these packages, so each PO4 is -3, but we have 2 of them, so what's the total negative charge? -6. Would you write that down with me? Guys, this is -6. So if the total negative charge is -6, the total positive charge is +6. Now, guys, the last step. We know that we have a total positive charge of +6, but how many nickels are creating that +6 charge? 3. So if it's +6, and if we've got 3 nickels, what's the charge of each nickel? Well, 6 divided by 3, 2. So this is, is it EL or LE? Nic, L, EL? This is nickel 2 phosphate. Now let's pause and think through questions. Yeah.
So unless it's like a 4 and a 2 or something like that, that 2 can just become the charge.
Unless it's what?
Like, so that 2 just can like on that red that you underline.
Here?
Yeah, that can basically become the charge that's going to be.
Oh, so you're saying this becomes this and this becomes that?
Yeah, because it's multiplied by 3.
Yeah, so Michael, that's a really interesting observation, and it's cool that you connected with that. Let me say this to everybody. So guys, Michael is noticing that there's a pattern. And guys, part of being good at science is finding patterns, right? And it's cool you see this. So the idea is that you're catching on to this idea that this is this. So it's like this is the charge of this, and this becomes the charge of that. That is true about 90% of the time. And so I know of high school teachers, even in this district, that teach it that way. They call it crossing charges. And so what they do is they talk about the idea that this becomes the charge of this, and that becomes the charge of this, and this becomes the charge of this, and that. And it actually works in these two examples, right? But it doesn't always work. And because it doesn't always work, I don't teach it, because I'd rather you understand the logic of it, and then you'll always be right. So I would be reluctant to say, yeah, do it that way, because there will be some examples of times it doesn't work. If you're interested, I can show you some of them, but it doesn't work all the time. So
like 4 and 2.
exactly, yeah, there's a great example. 4 and 2 doesn't work. Yeah, go ahead. Yeah. Exactly, yeah. So there won't be, except for one example. If you look at nitrogen element number 7, Kimball, it can be -2 or -3. Last time in class we agreed we're only going to use -3. So just underline that, and then that will take care of that one exception, and then they all only have one negative charge.
Okay, so what if the negative charge?
If there was what?
No negative charge?
It has to be, or else it's not really a salt. Yeah, because what's going to happen is the first one is a metal, which is always positive. The second one is the non-metal, which is always negative, so it's got to be negative. If it weren't, actually, if this weren't negative, then you'd have a molecule and not a salt, and that's what we're going to do on Tuesday. Okay, what else, y'all? You guys always ask great questions. Yeah?
You're always multiplying on the right side.
Always multiplying on the right, setting it equal, and then dividing on the left, every single time. You guys good? Let's do 2 more, and then let's get you going on homework, y'all. Come on. Oh, why is this so hard? Guys, let's try this one. I was going to turn you loose on this one, but I fear that's going to do more harm than good. So guys, step number 1, find copper in the periodic table. I don't remember, what number is copper? 20 which? 9. So guys, copper is element number 29. Does it need a Roman numeral? Heck yeah, it does. It can be 1 or 2. So guys, would you do this with me? So we're going to break this in half. Now we need the charge. But guys, be careful. We need the charge of what? Good. SO4, sulfate. So guys, please don't get ahead of me here. Sulfate is SO4 in the middle, the yellow sheet, middle bottom. Its charge is -2. Guys, stop. Now we're going to do some math, right? Abby got us thinking that we're always going to multiply. -2 times what? Not 4. 1. Guys, here's the deal. The ion is SO4. That whole ion has a charge of -2. There's only 1 of them. If there were 4 of them, it would look like this. Do you see the connection there? So guys, the idea is there is only 1 SO4. So this is -2 times 1 is -2. Yes? Now set it equal. This is +2. And now guys, +2 divided by 2 is 1. So what that means is this is copper 1 sulfate. Now guys, typically at this point I'll have people that are say, if it's a 1, do we need to put it? And the answer is absolutely. Guys, 1s are understood in the formulas, but 1s are not understood in the names. It's got to be there. Because without that 1, your reader wouldn't know whether to choose 1 or 2. You guys good? Questions there? You starting to see there's some little nitpicky details that you're only really going to master by practicing? Guess what we're going to do next? Yeah, practice. You guys good? Yeah.
Okay, so you multiply, instead of multiplying -2 by 4,
Mm-hmm.
you do -2 by 1. But what about like the top example?
Mm-hmm.
3?
Yeah.
Why didn't you...
That's a great question. And the answer, Abby, is because this is not polyatomic. That's a brilliant question. So why do we multiply by this 3? And the answer is, if we could see this, you would see an iron ionically bonded to 3 chlorines. So the ion is chlorine, and there's 3 of them, and each one of these is -1. The difference is this. If we could look at this, where can I draw that? Shoot, I just made a mess. I'm just going to clean this up. If we could look at this, what you'd see is this. You'd see a sulfur bonded to oxygens, and I'm not going to put all the electrons on there. And then this would be ionically bonded to a copper and ionically bonded to a copper. So the idea is that you have one SO4 and this whole thing is -2, and this has got to be +1 and this has got to be +1 for that to be neutral. But the other example over here, we've got an Fe that's +3, and then you've got a chlorine and a chlorine and a chlorine, and each one of those is -1. I don't know, there we go. Each one of those is -1, and that creates a balance in charge that way. So bottom line, without drawing the pictures, is this is the ion, there's 3 of them. If it's polyatomic, this is the ion, and there's 2 of them, or this is the ion, and there's 1 of them. So you're multiplying by how many ions there are. Here there's 3, each one's -1. Here's there's 2, each one's -3. Here there's 1, and each one's -2. Is that okay? All right, so guys, you guys, again, you ask great questions. Anything else on these? Can we just do the last one and just be done with this, and then you can get going on homework? All right, so guys, here we go. One last one. If I can get my board to cooperate, which apparently I can't. I'll probably click over here and things are going to freak out. Yep. And I go like this, and I go like this, and I go like this, and I go like this. All right, so guys, the last one we're going to do is MgNO3 and we split this in half, and then we find NO3 up on our yellow sheet, and NO3 is -1, and just like Abby got us thinking, -1 times 2 is -2, so this is +2, and the +2 is divided by 1, and so we come along and we go magnesium 2, and then NO3 is not nitrite, it's nitrate. And so and again, the idea is that there's this, each one of those is -1 times 2 is -2 plus 2, magnesium 2 nitrate. You guys good? It's completely wrong. Yeah, did you notice how I was hurrying and didn't make eye contact with anybody? Because I knew that somebody was going to catch me and I didn't want to let you. Guys, that's completely wrong. Why is that completely wrong? There's only one charge for magnesium. Guys, I did the same thing on purpose that you're going to do because you're either hurrying or you're just getting lazy. Guys, when you come over to the periodic table, right, first step, when you come over to the periodic table and find magnesium, you find out that magnesium can only have 1 charge. Yeah, I mean, it's 2, and we proved that. But guys, the point is putting that is wrong. It's unnecessary information in the same way that table salt is not sodium 1 chloride, because that's all it can be. So how do you avoid the problem? How do you do this right? Well, here's what you do. You look at magnesium, and you come over here, and you go, magnesium can only be +2. At that point, you do not play this game. You don't need to. Guys, all you've got to do is, if it only has 1 charge, you name the first ion, then the second ion is nitrate, and you done. That's it. Guys, please don't make that mistake. Y'all good? We done. So guys, grabbing your homework. We're now going to do the right hand. Oh, wait. Shoot. We're not done. Stop. Miss Call and Mr. Brown wanted to kill me last time because I didn't get to this, and I almost forgot again. Guys, we're not done. 3 minutes. You're at 2 minutes. So guys, we're good on writing names and formulas, right? And I know that if I hadn't stopped and gone back to this, one of you would have stopped me and said, hey, Mr. Neberger, we got to talk about this, so let's just talk. Because I know for some of you, the question that is burning in your very middle is, yeah, this is all fine and good, but do they dissolve in water? You were thinking it, right? Okay, maybe not. Take your paper and flip it over, your yellow sheet. Guys, next week we're going to do a lab where we're going to dissolve these things in water and react them together. And you actually need to know their solubilities. In AP, you memorize these. Don't drop the class. Guys, there's only 4 rules that you need to memorize, and it covers this entire table. It's interesting. With that said, you get the table. So, guys, what you've got to be able to do is use this table in order to figure out whether or not these dissolve in water. So let's figure this out. Guys, what do you see across the top of this table? What are those things up there? Those are the anions. Those are the negative guys. What do you see down the left-hand side? The cations, the positive dudes. And guys, if you've got a cation and an anion and you bring them together, you then can figure out their solubilities. So let's talk about what they mean. S means soluble. That dissolves in water. I means insoluble. That does not dissolve in water. It just falls to the bottom and sits there. D means decomposes. For our purposes, it looks exactly like dissolving. And then a dash means that that compound does not exist. So guys, what you've got to be able to do with that is play... I'm about to cuss. So guys, what you've got to do with this is you've got to be able to play this game. And actually we should write this word down. Sorry guys, I forgot about this. You need to know the word precipitate. That's the only thing you need to write down from this slide, but do it with me. So, guys, salts that don't dissolve just sit on the bottom. Those things that sit on the bottom we call precipitates. Technically, the word precipitate means to change phase in the same way that we call rain precipitation because it's going from a gas phase to a liquid phase. Well, if we have salts that don't dissolve in water, they go from the solution phase to the solid. We call it a precipitate. Anyway, so guys, what you've got to be able to do is this. Do these things dissolve in water? Let's just stress test this table and then we're done. Potassium hydroxide. Does it dissolve in water? Look it up. Yes or no? Find potassium on the left. Find hydroxide on the top. Bring your fingers together, column to row. And what letter do you see? You see an S. What does that tell you? Oh, wait. Yeah, it does dissolve. So, guys, what does that tell you? It's soluble in water. Guys, do this with me, though. Let your eye scan across the entire potassium row. What do you see? They all dissolve in water. And guess what, guys? All of the alkali metals dissolve in water. Hey, this is the stuff you're going to learn in AP. But we're okay. Are you good on the idea? Let's do 2 more. COCl2. Now you've got the formula. Does that dissolve in water? You find cobalt. You find chloride. You bring those together. Does that dissolve in water? What letter do you see? S. That means it's soluble. By the way, if you allow your eye to scan down the entire chloride row, what do you see? Mostly S's, right? There's a couple I's. Silver, mercury, and lead. Are those there? Those are actually the rules. But we're good. So guys, let's do one more. You just need to be able to use the table. What about this? FeC2O4. Does it dissolve in water? You guys are silent. What's going on? Which one? Because guys, if Fe has a charge of +2, does that dissolve in water? I don't remember. No. But if it's +3, then it does. So which one are we looking at? Well, guess what we have to do? Break it in half. What's the charge of C2O4? Oxalate. What's its charge? Come on, y'all. C2O4 is -2. How many of them are there? What are we going to, guys, you learned this. You said, yeah, we're good. We can figure out Roman numerals, and now you're cramping up. Guys, we got to figure out the Roman numeral for iron, so we break it in half and work it backwards. Oxalate's -2. Is it -2 times 4? No, because there's only one oxalate. So this is -2, and this is +2, and it's +2 divided by 1, so what's the charge of the iron? +2. Now look it up. So if iron is +2 and it bonds to oxalate, does it dissolve in water? What letter do you see? I. Does that dissolve in water? It does not. Therefore, it would precipitate. It would sit on the bottom as a solid. You good? Okay. So guys, do this with me. Grab now your homework packet. And guys, as you're now looking at your homework packet, we are now going to do, guys, the right-hand side. You guys want to do odds or evens? Mixing it up. We're doing odds. But guys, let me show you this then. You don't need to go back and do this for the left-hand side, but you need to do this for the right-hand side. Fill in the stuff in parentheses. But guys, here's the deal. This solubility table on the back of this sheet is not very exhaustive. We're missing a lot of ions. For example, the sheet does have lithium, I believe. Does it have lithium? Nope, lithium's gone. So guys, it doesn't have lithium. Therefore, you're just going to put Ng for not given. So if you run into things that they're not on that solubility chart, don't put it. But for the rest, you're going to put it. So guys, what about the P on ammonium oxalate? That means partly soluble. So just put down the letter that you see there. So guys, that's our work for today. You'll get it done today. I'm not going to I'm going to get rid of this. Guys, I strongly encourage you to work on this homework. Just a second. I strongly encourage you to work on this homework without looking at the answers. Check periodically, like every 5. But guys, we're going to do the right-hand side. Did we say odds or evens? Odds. And we'll grade these on Tuesday. Yeah, Kimball. The upper right-hand drawer. Just the evens. Yeah. Would you, Martina, do you need one as well? Kimball, would you walk one back to Martina, please? All right, y'all, we're done. Dig in.